this video, we'll use the data trace feature to measure position settling time, position error, and torque ripple. Hi, I'm Matt Pelletier. Here's a quick preview of how to use the data trace function in Sigma-7 Plus version 7 to accurately measure the servo system response to the worst case move profile. First, you set up the trace to properly capture the response of the program jog test move. There are three measurements important for servo tuning that we will focus on. Position settling time, which is how long it takes the motor to settle into final position. Position error, how far behind the command the motor is during the move. And torque ripple, which is how much the motor is vibrating during the move. So follow along with me and let's get an accurate baseline measurement of the performance of the x-axis on the demo. So you see here I am connected to the x and y axis on the dual axis amplifier, and we'll be focusing on this x-axis motor. Before we can do any data trace, we need to have a move to trace. We had set up the program jog in a previous video on the z-axis, so let's do the same thing, same exact move on the x-axis, and we can't forget to also set PN 520 so we don't get that position error overflow alarm. Alright, so we'll edit the parameters and go to the PN 500s and set PN 520 100 times higher with 2 zeros. Write those in. I'm going to close it. Save. Okay. Now under the menu, I'll go to Program Jog for Axis A. Okay. And our numbers were 16,777,216,0. That's 10 rotations at rated speed 3000 RPM in 35 millisecond XLD cell with 1 second between moves. We'll put in a 0 for infinite number of times. And here we see the move. Let's be sure that runs. Servo on, execute, and I see that is running. Just to manage my screen real estate, I'm going to move this window over. And that gives me a nice little view now. Now we can open up the trace feature for the x-axis, axis A, trace. Just for a quick overview, I think you can see already that we're able to use the trace feature along with program jog. And also, if you had the IEC controller or any controller commanding motion, you'd be able to trace the response of the motor. We'll see later on that we can simultaneously trace both of the axes. If you're using the dual axis amplifier, you can trace both at the same time. And I'll show you guys how to zoom and use the cursors. And later on, we'll use the continuous trace mode, which just keeps refreshing the trace of a repeating move. We've got buttons for history of saved traces, and you can overlap different traces that you've saved to see the difference in the response as you progress through tuning. If there's too much on the screen, you can hide some of the data that's traced, make it a little bit easier to see. We'll show you that. And I should just make it clear that we're recording the response of the motor, and we're not recording anything to do with the controller itself. So if you want to see the data of the controller, you need to go into the controller and use that software, MotionWorks IEC. We will not be able to see any of the variables or any of the motion as is perceived by the controller. This is the exact response of this motor with this load. So the first step on the trace is to go to the setup, click the setup button at the top right. And there's a lot to set here, isn't there? But we make it easy with this auto setting. If you get familiar with these auto settings, then you really don't have to fill in all the other fields. One of the settings that I use the most often are these two here. It checks position reference and monitors positioning from the start. The way to use it, you select it, and then a very important step, click the Set button. When you click Set, that sets the other fields. If you don't click Set, it leaves them how they were. So if you want positioning from the start, click Set. You can see it traded out data 3 now as position error. If you wanted position reference, and click set, you have different data. It sets up the trigger. The one thing you will have to estimate is the total time of the trace. The amplifier itself is storing 1,000 data points of all of this data, 3 channels of numeric data and 3 channels of I/O data. The trigger setting tells it when to start collecting the data. The data will be collected on the amplifier in real time, high speed. There's a memory area, but you just need to tell it how far apart to take the samples. So right now, by default, you probably have 125 microseconds times 1,000 samples gives you 125 millisecond total time. So by trial and error, you just need to estimate how long to make this sample time. And let's bump this up a little bit here to 625. And that's the basic settings that you need. The auto setting, the set button, and the sample time. Let's click OK, and then click Start. And this is the default response of the motor. So what are we looking at here? We have the position reference speed in green. This is the perfect trapezoidal profile that we've generated from program jog. This is the input to the position loop, seen as a speed. We have torque reference. That's the torque command into the motor. And channel 3 here is feedback speed. It's the actual speed of the motor as viewed by the encoder. So you see it doesn't exactly match the command. Doesn't necessarily mean that's a problem, but that's what we observe. If you have any trouble with the colors, you can go to the data or the I/O tab and use display or hide, and you'll see which channel 1 and which is channel 2. I'll be working with them all at default. First thing we need to do now is to use the magnifying glass to zoom in, and what I'd like us to do is to measure the acceleration time of the command signal. If you recall, we had set that to 35 milliseconds. To zoom in, go to this magnifying glass icon, click on it once, and you'll now draw a rectangle with your mouse over the area that you would like to fill the screen. So I have drawn a box over the acceleration area, and now I see a close-up of that acceleration command, the torque, and the feedback speed. And I want you to measure how much time it is from the beginning of the acceleration command to the end of the acceleration command. You can do that with the icon to the left of the magnifying glass for cursors. Let's click on the cursors icon. You hover your mouse over cursor A, it turns into a hand icon, and you can move that over to the beginning. You see the position now of the cursor, cursor A. Do the same with cursor B. Click and drag. Now you see the position of A in time and B minus A, 35 milliseconds as expected. The frequency is also given here in case you're measuring a sinusoidal waveform, peak to peak or valley to valley. You could estimate the frequency with these cursors. Now, sometimes when you zoom in, you'll end up making a mistake and you can't see anything. All you need to do is click the negative zoom button, and that'll completely zoom you all the way back out again. So that's how I recover from that. But it is important that you use the zoom and zoom in to get the most accurate measurements. And that you don't try to make all your measurements with the cursors, really close together, because one little pixel can make a big difference then in the measurement. Now, if you would, please take a little time to be sure that you're comfortable with zooming and measuring on this trace, and that you are able to use the setup and the start, and then we'll continue. This tuning results table shows where we're going with the training over the next few videos, and we'll want you to measure and record the values for position settling time, maximum position error, and torque ripple for the x-axis, and that will serve as a baseline measurement by which we can compare the results that we get in the following videos on tuning lists, advanced auto tuning, and custom tuning. So if you could go to your class materials folder and pull up the tuning results table, I'll be looking at it in a PDF viewer. You're welcome to print it and use pen and paper, or many PDF viewers have a typewriter feature that lets you type right over the PDF. And the first measurement of interest is called position settling time. Position settling time is how much extra time it takes the motor to stop after the end of the commanded move. It's really important to make this as low as possible, hopefully 0, if you're trying to have a very fast cycle time in a point-to-point application. The signals that you need in order to accurately measure this are the position reference speed and a signal called coin, which detects when your motor is within a certain distance of the target position. We need to measure from the end of the position reference speed to where the coin signal goes from high to low. Now back on our trace, we do have position reference speed. We can take a cursor and put that at the end of position reference speed. And we also do have the coin signal, but you notice it's not going low, which means at least for the time displayed here in this trace, the motor is never quite in position. But what does it really mean to be in position? When does that coin signal turn from high to low? What are the condition? Well, the condition is set by a parameter, PN522, and that's a parameter with the units of encoder pulse when you're using the MPIEC controllers. So if you look at this graphic at the bottom, coin is telling you when the motor's feedback position is within plus or minus the number of encoder counts in this parameter PN522. The way it works in time is kind of like this animation. The controller is giving the position over time, and the servo is somewhat behind. It's exaggerated here. But as soon as the feedback position gets within this position complete width, sometimes it's called position complete window, then this coin signal goes from high to low. Therefore, you really cannot measure position settling time unless you have first considered the setting of the position completed width for the coin signal, PN522. So what do we need to set it on for our motor? Well, we're working in degrees. And if we take the number of encoder pulses per rotation of the motor, divide that into 360, that's 46,603 pulses per degree. And let's say that we just arbitrarily want in position to be 1/10 of a degree. We then need 1/10 of this value, and we get a value of 4,660 encoder pulses in 1/10 of a degree. So we need to go to PN522 and set it to 4660. And then we'll be looking at in position of 1/10 of a degree. X-axis menu, edit parameters. Need to move some of these windows out of the way. And I'll go to the sequence category, PN522. Look, we're only at 7 encoder counts. There's 16 million per rotation. That's a pretty tight tolerance right now. 4660 for 1/10 of a degree, and write that parameter in here. The motor's still running. Now we need to capture a new data trace with this new value for the coin signal level. So let's click start again. I will not save. And now we see that the coin signal goes from high to low. So meaning at this point in time, right here where the coin signal goes from high to low, the motor is within 4660 encoder pulses, or 1/10 of a degree, from the final move position. All right, so you have cursor A at the end of the move where the position reference speed goes back to 0, and the distance between cursor B and A, 234 milliseconds. So we do the move, and it takes the motor an additional 234 milliseconds to actually reach the final position within 1/10 of a degree. This is the position settling time for this axis with this move. Let's go to our table then and write that in there. We had 234.8. I'm going to round that to 235 milliseconds. And it is important for you to be able to measure this manually, but there's also the option, if you have just one move and you have all of the data, the trace feature can measure this for you. If you go to the setup, again, I won't save, and at the bottom left, the display option for settling time, that's really the only option there is right now. Check that box, and OK. Now, when you trace the move, motor's still moving. See, it's doing an automatic measurement. And it got pretty close to what I had before, 237 milliseconds. This automatic measurement can save you a lot of time once you know what you're looking for and how to measure this settling time. Now let's measure the position error. Position error just shows how far behind the motor is at different points in time during the move. Ideally, you'd like that position error to be very low. It's especially critical in applications like electronic camming, electronic gearing, where it's not so much the end position that's important in the servo control, but instead that the motion path is followed exactly, or that the slave axis is truly following the master axis with the least amount of error possible. Position error can be traced directly, so you really just need to be sure that position error is in your trace setting. And additionally, position error can get pretty high since you're measuring it in encoder counts. So you'll want to check a box called high precision trace. You see that we don't have position error right now selected. So we'll go into the setup. I'm not going to save. And if you choose the auto setting, scroll down a little bit here to monitors positioning from the start and click the set button. Now data 3, instead of being speed, is position error. When you measure position error, it's recommended that you check the box for high precision trace. Now this doesn't mean that it's more precise from a positioning standpoint. It means that double precision, high precision 32-bit integer data will be captured, and as a result there are now only 500 samples available in the data capture memory of the servo. So let's double the sampling time to 1250 so that we still have that 625 milliseconds so that we can see the whole move like we saw before. Okay. And start. Motor is still spinning. And here we have our trace. And here we see the position error. It goes very high. In fact, at this time, the trace function is not able to display the true value that's recorded. But the maximum value we can see here is 1.5 times 10 to the 7th. The way to measure this would be to go to horizontal cursors. Put one cursor down at the bottom and the other one up at the top. And we're measuring on channel 3. So the difference between those cursors is 1 times 10 to the 7th. All right, so we can put that in here for maximum position error. 1 times 10 to the 7th, and that's pulses. So right now, the position error is pretty high. It's over 1 rotation. And as we proceed with tuning, of course, we'll see this value go down. As a little aside on position error, you can still see the data, even though it's not displayed here completely. And you can do that by exporting this data as a CSV. And then you can open it like I've done here in Notepad, or maybe Excel would be better. And I see here that at millisecond number 211.25 milliseconds, the error was 20,739,904. Either way, the error is very high, and that's the conclusion here. But remember, in tuning, the question is always, is the response acceptable? And although the error is very high, still the response may be acceptable. Now let's look at measuring torque ripple. Sometimes it's also referred to as the noise on the torque signal. You'll need to zoom in at the torque reference signal and attempt to measure the peak-to-peak or estimate the peak-to-peak high-frequency noise that you see on that signal. We should choose a place on the trace where there is movement and motion in the machine, such as right here where we know the motor is moving, and you'll need to zoom in. You may need to zoom a few times. Let's take the magnifying glass and zoom in on that portion of the torque signal where the motor is moving. Zoom in some more. I'm just going to keep zooming in until I see the noise of the torque signal. So based on this graph, I would pull up my cursor as horizontal because we need to measure the amplitude. And I'm going to put the cursors in such a place that it's the average of what we see is this oscillation on the torque signal. You can't make the cursors go diagonally. And I'm seeing that channel 2 torque reference is about 0.82%. When you measure the torque ripple, you can get a better result by having the highest sample rate possible. So let's go to our setup and get rid of this high precision trace now that we're looking at torque reference. And let's reduce the sampling time. Maybe we'll get part of that move. And if we can sample the torque at 125 microseconds, I think we'll get a better picture of what's happening in the torque loop, since the torque loop is a very fast updating loop. Okay, my motor is still running, and we'll hit start. Okay, so now here's the torque signal, and the motor is in motion at this point in time. So let's zoom into that same area now. You see we have a much finer resolution than we did before. Maybe I'll just look at one part here, put the cursor on. I'd say this distance between the cursors represents an average of the peak-to-peak of the torque waveform. I'm getting 0.37. Probably we're safe if we even go as high as 0.5. And I'll use 0.5% in my tuning results table. 0.5%. That's a percent of the motor's rated torque. Okay, so I think we have a pretty good idea of the baseline performance of the x-axis with the default tuning-less tuning algorithm. The position settling time, 235 milliseconds. Pretty high position error, but the torque ripple, the noise is very, very low, nice and smooth motion. And we'll progress in the following videos then to see what we can do with tuning-less, advanced auto-tuning, and custom tuning. And you see that you'll be measuring this quite a number of times as we go through tuning the rest of this axis of the demo. And we'll skip that for the y-axis. Just do advanced and custom tuning on the y-axis. And for the z-axis, we'll have you measure it under default. And for that one, we'll skip ahead and do auto-tuning and custom tuning. And as we tune this demo, what I'd like to propose is that we tune the two motors on the left, X and Y, to optimize for lowest position settling time. At the same time, I would like these axes to be synchronized with each other, so that if given the same command, they'll do the exact same move. On the other hand, let's have the motor on the right be tuned for the lowest position error. Maybe this is a camming or gearing, a rotary knife type of application, where perhaps this axis would be ultimately synchronized to an external axis that it must match exactly. And we will go through this process as we proceed through the different videos in this series of training on Sigma-7 tuning. Thank you for watching this video. For more information on Sigma-7, please go to yaskawa.com. Products, Sigma-7 Servo products.